All right. So yeah, let's go into the topic of GNSS denied absolute visual localization. And this is an application example of where one might apply AI in drones. In this presentation, I will first very shortly talk about Saab, what they do in particular in Finland. And then I'll go into the case example of GNSS denied localization. So if we first start with Saab, what kind of a company it is, Saab has a very broad product portfolio ranging from fighter jets to various weapon systems. And I represent a part of the organization that's responsible for sensors. Here in Finland, we have quite a broad portfolio of research and development actions. So when it comes to research, we are participating in various EDF and Business Finland programs, as well as some others. And also we have a long-term research program in collaboration with Aalto University, where there's been up to 8 simultaneous PhD projects ongoing. And the results that I'm showing on in this presentation relates to my own PhD, which I did in this program. Besides research, here we do product development, and relatively recently we launched this Sirius compact product line of radar electronic support measure sensors. We also develop subsystems for other Saab products, as well as deliver projects to the local customer. Okay, but let's move on into AI in drones. So the application example that we are considering today is related to drone localization. So we've all learned from the media that global navigation satellite systems are easily jammed. So how can we cope without them? The approach that we are considering here is to use absolute visual localization. And what that means in practice is that we have a drone that's carrying a bunch of sensors. There's a camera, an inertial measurement unit, and a magnetometer, and we use a satellite image or an orthophoto of an area as a map. So just to give you an intuition about what the problem sort of looks like, you can see on the left a video recorded from a drone. And now the question is that with the sensor data that's available, how can we infer where we are with respect to this map? And the size of the map can be, for instance, 10 by 10 kilometers. The particular problems that we need to address include how to tolerate differences in appearance. So, for instance, here on the left, we can see that the flight takes place during the winter, whereas the reference map is recorded during the summer. And we also need to survive some natural ambiguities. For instance, on the left, we see that the drone is currently on top of a forest, but on top of exactly which forest on the map are we actually looking at? And finally, how do we make everything work on a limited capacity computational platform? So my proposal is to take 2 steps. So the step number 1 is to leverage first principles reasoning before applying AI. And step 2 is to apply AI where first principles reasoning falls short. Okay, so starting with step 1. The very back end of the localization solution is very well known from let's say, from decades ago in robotics applications. So let's take a quick glance at that back end, and that's called Bayes filtering. So let's consider a one-dimensional example. So we have a robot, the red rover, that's moving along a long corridor, and that's the blue wall, as well as some doors shown on top. And let's say that initially we don't know where the robot is with respect to that corridor, but we have a map of the corridor, and then we can also make some measurements with the robot. Our belief on where the robot is with respect to the corridor is plotted in the middle. So initially it's a uniform distribution. We don't know where we are. Okay, so what can the robot do? Well, it can observe its surroundings. So we can make an environment measurement. So let's say that the robot notices that there's a door right next to it. All right, so what does it mean? There's 3 doors on the map. So it can be in one of those three locations. So let's update our belief accordingly. So now our belief reflects that we are in front of one of these three doors. Okay, what kinds of other measurements can the robot do? Well, it can measure its own movement. So let's say that the robot moves a little bit. Then it can measure how much it moved with respect to an earlier moment in time. However, this measurement is not super accurate. And now what we can do is we can combine this different type of measurement, this odometry measurement, with the previous belief. So we shift our belief to the right according to the movement, and then we get this kind of a belief on the position of where we might be. So what the robot can do next is it can observe its surroundings, so it can make an environment measurement. And let's say that the robot sees a door again. So now we can infer that we are in front of this particular door. So this is the type of classical first principles reasoning that goes on in the back end. So in order for this to work, two components are required. We need an odometry approach. For this, we use first principles reasoning. And then we also need a way to relate the environment measurements to the map. And for that, we use AI. Okay, so let's continue with the odometry measurement. So what odometry means here is, well, it's visual inertial odometry. So what it means in practice is we track some landmarks that are easily observable from a sequence of camera images, and then we fuse the movement of those feature tracks across the image plane, as well as inertial measurements. And with these measurements, what we can do is we can measure how much did the robot move with respect to an earlier moment in time, and we can also resolve where those feature points were with respect to the robot. Now, one additional step that we can do in terms of first principles reasoning is that we can make the arguably bold assumption that the ground beneath the drone is flat, and then we can fit a quasi-ground plane to the detected feature positions or estimated feature positions, and then based on this knowledge of where those feature positions are on the ground, we can make the camera image look somewhat similar to what an orthophoto or a satellite image would look like. And this is the environment observation that we will use in the localization. All right, then moving more towards the AI part. So what we've done so far is we have established a way to do odometry measurements, and we have also done the best we can when it comes to classical measures in order to make the observation by the drone look as similar to the satellite image as possible. However, there are still some remaining challenges that are quite difficult to encode in first principles reasoning. For instance, seasonal appearance difference. On the right, you see the same building on top right, you see the same building imaged in the summer and in the winter. And then you also see a map image on the bottom. So now the question is that how do we know or how do we let a piece of software know that these represent the same area? And the second challenge is that how do we find the position of the drone over a very large search area? So let's say that we are considering this 100 square kilometer search area. How do we go about this? Well, here is one example approach that we might take. So what we do is we train a neural network that takes in an auto-projected image, and then it goes through a neural network, and the neural network produces an embedding vector. And now this embedding vector represents this image in some meaningful way. By training this neural network in a convenient way, which is called contrastive learning, we can create a neural network that produces embedding vectors which have characteristics that are beneficial for us. For instance, we can train the neural network to create embedding vectors that lie very close to each other in the embedding space, if those images correspond to the same area. And also we can force the neural network to create an embedding vector that exists very far away from another embedding vector if those two vectors represent different areas in a satellite image. So this approach is called contrastive learning, and we use triplet loss. And the data that we use for training this model consists of satellite images. So what we can then efficiently do is that we can measure image similarity via a distance measure in the embedding space. So the end result with this approach is that we get a very compact representation that allows us to store large maps. We also get a very fast similarity evaluation approach, and that allows us to explore large hypothesis spaces. So thereby we get somewhat efficient computation and storage. So how do we go forward from the neural network? Well, what we do is offline we build a map using the neural network consisting of these embedding vectors. We create the map, for instance, with a grid of 10 by 10 by 10 by 10 meters by 6 degrees. And then during flight, let's say every 100 meters or so, we acquire an image of the terrain below the drone, and then we use that as our environment measurement. And now every 100 meters or so, we can measure the similarity of the embedding vector by computing the, for instance, Euclidean norm between this embedding vector and the vectors in the map. And this is an approach that is presented on this paper that's shown on this slide. You might recognize that Ville Kyrki was my supervisor during my PhD. Also in my PhD thesis, there's more details on this approach. So then once we plug everything together, let's take a look at how it works in practice. So let's have the UAV fly a little bit. And then let's pause the video. I will first explain what each of these small images mean in this presentation. So this shows the UAV image, and this is the ortho projection of the UAV image. And we use this ortho projection as the environment measurement. So meaning the measurement that we use for correlating it with the map. Here is a picture of the original map. And then this picture shows a sort of a heat map or a likelihood of what is the likelihood that the ortho projection matches that area on the original map. So for instance, with this image, we can see that the forest areas seem to have a high likelihood. And then this image shows the probability of state. So that is our belief of where the robot is. At current stage, our belief is quite scattered, so the robot might be in any of the yellow-colored places. And then this plot shows the lateral translation error of the drone as it is flying as a function of number of updates, and we do an update every 100 meters. And then these small images show zoom ups or close ups near the ground truth, and the ground truth position is shown in red color. So let's have the drone fly forward a little bit. And then we see that after some, let's say, well, approximately 20 updates, our solution converges very close to the true pose. So the error goes down to as little as about 20 meters in lateral translation error. And after it has converged to this level of translation error, it seems to track the location quite well, despite the ambiguities in the environment. So there's lots of forests and fields and those kinds of things. And also despite the appearance difference of how different the UAV image is from the original map. So to summarize, for AI in drones, my proposal is to first leverage first principles reasoning before applying AI, and then apply AI where first principles reasoning falls short. In implementing AI approaches on drones or whatever the use case, consider edge computing and storage capacity restrictions, size, weight, and power, and cost. And also consider projecting your problem into a domain where representative data is plentiful. So for instance, in this case, instead of operating on the drone images, what we did is we sort of transformed the observations of the drones into a domain that resembles satellite images, and that sort of bootstrapped our AI training approach. All right, this concludes my presentation, and my contact information is shown on this slide in case you want to be in contact.